section 4 on conditional probability. So this section gets a little tricky, so we'll go slow and try and cover all the definitions and examples, but this is where things get a little confusing for people, so we want to take our time with it. We'll start off with the official definition. Here it is, conditional probability. Well, it involves the notation, first of all, I guess, because we covered the notation. So the notation, the probability of F given E is read just like that. The probability of event F given event E. It is the probability the event F occurs given that event E has occurred. Nice? Okay. So it is the probability that event F occurs given that event E has occurred. So that's one description of it. I'm not sure if it really does a good job of really explaining what things are. It might be still a little confusing. So we'll go through some examples, and then when we refer back to this, hopefully this will make a little bit more sense. So to try and explain what that's trying to tell us, let's look at this example. Let's say we go back to Vegas, right? Keep going back to the same well, betting. So we got a situation where a dealer is going to roll one six-sided die. So a simple game, he rolls a six-sided die, and you're just betting money on what the result of that six-sided die is going to be. You can bet something simple, like it's going to be a 6. You can bet something like it's going to be an even number, an odd number, something like that. So let's say that we have 2 players. Player 1 is going to bet money that the die is going to come up as a 4. And player 2 bets that the die is going to be an even number. Okay, so those are our 2 events. Let's write it down. So let's say that we have, so the experiment is going to be that we roll a 6-sided die. The sample space is all the individual values of 1 through 6. And then we have 2 events. Let's call this event A is that the die is a 4. And event B, we're going to say that the die is an even number. Okay, good. So player 1 bets some money on A. Player B bets some money that it's going to be even. So let's look at a couple of situations. First of all, let's think about a Venn diagram for this guy. So there's a couple of ways that we can draw a Venn diagram for this situation. So we have a big rectangle like this, sample space. And so let's say that we have event A and event B like this, event A and event B. Then, for instance, event A, that it's a 4, well, okay. And event B is that it's a 4 or a, well, it could be a 2, or it could be a 4, or it could be a 6. Right? Those are all the ways in which event B can occur. So this can be drawn as a 4 or a 2 or a 6 this way. Right? Clear? Clear, clear? So the 4 is part of B, but it's also part of A. And in fact, in this particular case, it turns out that there are no numbers over here. So I could draw it this way, or I could also draw it this way. In this particular case, it turns out that event B is like this, and event A could be seen as a little subset of event B. Right? So now I could say that the 4 is in there, and then there's a 2 and there's a 6 in there. So you can draw it in either way. Good? Okay? And then remember, it's a sample space, so all the other options are also on there. So 1 or 2 or 3 or 5, those are also potential winners. I'm sorry, not potential results, potential outcomes. And then same thing over here, we could include the 1 or the 3 or the 5. Is everyone with me so far? Good, good, good. Okay, so then player 1, thing says that player 1 wagered money that the die was going to be rolled and it was equal to a 1. So the probability that player 1 wins is equal to the same thing as just saying probability that event A happens. Okay? You know, again, notation. Sometimes it's useful to write it all out, and sometimes it's useful to cut down on all the writing and just get down to something a little bit more streamlined. So player 1 wins. That's the same thing as event A happened. We rolled the dice, and it was a 4. Player 1 wins. What is the probability that that happens? Easy, right? We've been doing this a lot. We know what that is. This is going to be equal to the number of ways in which A can happen divided by the number of ways in our sample space. The number of outcomes in our sample space in the denominator, the number of outcomes in our event A. So from just counting things, there's only one way that a 4 can be rolled, a 4, it's a simple event. And this guy is a 6. I know that answer should be 1 out of 6. We're good? Everyone's with me? All right. What about the other case? Player 2 bet that it was going to be an even number. So the probability that player number 2 wins is equal to the probability that event B has occurred. And as before, then this is equal to the number of ways in which B can happen divided by the number of outcomes in our sample space. And so how many outcomes are there in event B? There's 1, 2, 3. So this is a 3 out of 6. Everyone's still with me? Okay. So here's where conditional probability comes in. Again, kind of picture this scenario. We're in the casino. This is the hottest game in Las Vegas right now. So I'm at the table, and I put money down on 4, and then my friend, he puts down money on even, right? But it's a very popular game. Everyone's dying to put their money on the table, and then people are betting this and the other, and they're taking a long time. And I got to go to the bathroom. So I'm just waiting, like, come on, go ahead. Can you roll it already? I can't wait. Forget it. I got to go to the bathroom. So I take off. I go to the bathroom. While I'm in the bathroom, the game actually happens. The dealer rolls the dice, and people win, lose, whatever, cleans up money, whatever. I come back from the bathroom. I find myself like, did I win? What's happening? What's happening? Am I rich now? And my friend says, I won. He won, okay? So he doesn't know if I won. He's just worried about himself. Woo! I'm a winner. Okay, but what was the answer? What was the roll? What happened? I don't know. All I know is I won, man. That's all I care about. All right. So now I have to go find out whether I won or not, right? So we are not repeating the roll. The roll already happened. There was only one time that it rolled. There is an answer out there. But what do I have to do now? I have to go to the pit boss and tell them, hey, I put money down, I left, this and the other. So they're going to have to go look at the cameras and all that. While they're doing that, I get to recalculate my probabilities of winning. Now that I have new information, right? So we are not rolling the dice again. It only will happen once, but now I have more information because I know that B definitely happened since I know my friend won. Okay. Are you guys with me so far? I know it's kind of a convoluted story, but I think it helps understand what this whole conditional probability thing is about. So this is what I want to find out now. As I'm standing around waiting to find out what the real answer is, right? They're looking at the footage, they're looking at the cameras and all that. While they're doing that, I'm sitting there and I pull out my calculator. I'm like, okay, before any of this happened, the probability that I was going to win, the probability that it was going to be a 4 was 1 out of 6, right? But now I'm thinking to myself, I know that he won. How does that affect me? So I want to know, what is the probability that player 1 wins, given that now I know that player 2 wins. Well, 1, I guess. Player 2 won. Right? This is fixed. We already know that happened. He's already celebrating over there. I know he won for sure. I don't know about me. How does his winning affect me? So I got to recalculate that. So the first way we're going to do it is by just looking at our Venn diagram and examining that situation. And then we'll go back and try and come up with an equation and see where the equations from this chapter come from and how they make sense based on what we assumed them to be. Okay, so now think about it. If I know he won, I came back from the bathroom like, hey, what was the answer? He could have just told me, yeah, it was a 2, I won. Or yeah, the dealer rolled it, it was a 4. Oh, great, we both won. If he told me what the actual answer was, then I would know, and then we'd be done. But he didn't say that. He just said he won. So is it possible the dealer rolled a 1? No, because he won, right? So it's not possible that it was any one of these three. I've narrowed down the scope of the possible answers. The possible answers are one of these three now, right? Okay? And of those three, how many ways are there for me to win? 1 out of the 3. So the answer should be 1 out of 3. Is that clear? Okay, so we'll like I said in a second, we'll go back and try and come up with an equation for this, even though right now, based on my Venn diagram, this is what I think the answer should be. And everyone's clear on that. Good? What if it was the other way around? What if I came back from the bathroom and was like, hey man, what happened? Did I win? Am I rich now? And he says, I don't care about you, man, I lost. Right? So he doesn't tell me what the answer is. He didn't tell me what the dealer rolled. He's just telling me about himself. He lost. So, how do we describe that? So what's the probability that player 1 will win, given that I know for sure that player 2 lost? What can I say there?
Wouldn't you lose too?
Wouldn't I lose too? Of course, because if he lost, then that means that one of these things happened. It was either a 1 or a 3 or a 5. That's how B lost. And if it was one of those things, it absolutely guarantees that I lost too. So I know the answer to this should be 0. There's no way that I won if I know that he lost. Okay. So notation, again, whichever makes sense. Sometimes it makes sense to leave it in little words like this so we can see what we're talking about. And sometimes it makes sense to bring things back to the letters that describe the events. So this guy over here can also be written as the probability of A given that B has occurred. Right? A was player 1, player 2 was B, and we know that the answer to that is 1 over 3. And also here, this is the probability of, and now this is where we have a little bit of variety. We can write A given, and then we want to say that player 2 lost. How do we describe that? Well, that could be described as the complement, like that. It's the complement of B, right? It's the opposite of B. This is B is that player 2 won, so B complement is that player 2 lost. So we can write it like that. Or we can also write it as probability of A given that B with a bar on top. B with a bar on top is the same thing as B complement. And then one final way, some books like to use the probability of A given, and then they just write the word not B. So B complement, B bar, not B, they all mean the same thing. They're all trying to describe that. And in all of these cases, the answer we know is 0. If I know for sure player 2 lost, I lost as well. Any questions so far? Questions? Okay, so let's make some room here. Let's push this over. Let's keep that Venn diagram. So I'm just going to write one of the Venn diagrams. Let's keep the one where they're overlapped. So this is B, this is A, and we have this one as a 4, 2, and 6, right? Even. And there's a 1, a 3, and a 5 out there. This is our S value. Okay. So let's get back to the results of the probability of A given B. Probability that A won given that B has won. Given that B has occurred. So we saw that the answer was 1 out of 3. How did we get that 1 out of 3? So that we know that the answer is that, for sure. Okay, so first of all, let's look at the 3. How did we know that there are 3 possible things there? Okay, well, if I know B occurred, as we said, we know it was not one of these, right? Because B occurred. B happened. So it can't be that the answer was that the dealer rolled a 1, a 3, or a 5. It had to be true that the dealer either rolled a 4, a 2, or a 6. So that's where that comes from. So this is equal to the number of ways in which B can occur. right? If I know B definitely happened, player 2 was definitely a winner, then I know that it had to be one of the ways in which B occurs. So there are 3 ways that can happen. And now, if I know he won, the only way I could win is if both of us won, right? At that point, if I know he won, the only way I could win is if we were both winners, right? So, this one right here refers to the number of ways in which A and B occur, which is that guy, the 4, right? At that point, since I know he won, right, that means it was one of these, a 4, a 2, or a 6. I know he won, it had to be one of those. Now the only way that I could win is if it happened to be the one case where we both won. Good? Okay, so that takes us back to the general formula for this thing. So right now I was tying it into this particular example, but in general we're just going to say that probability of A given B is equal to the number of elements or number of outcomes in A and B divided by the number of outcomes in B. The order is important though, so look at the matching. Here it's given B. B is the thing that definitely occurred. There's no doubt about that. That one is constant. I'm concerned about the probability of A. This is where there's randomness. Did A happen, given that we know this one happened for sure, and this matches with this guy down here. Okay? Good? Good. Okay. So now we're going to do a little bit of algebra magic. Anytime you have a fraction, you can multiply the numerator and denominator by the same number and get the same fraction, right? So if I wanted to, for no particular reason, I could multiply it by 3 over 3, right? And I get the same equivalent fraction, right? If I wanted to. There's no reason why I chose 3 right now. It's just a random number. If I wanted to, I could choose to multiply this by a decimal, 0.25 and 0.25 if I wanted to. That's another version of 1, so I can multiply this whole fraction by this, and I get the same thing, right? I get an equivalent fraction, I should say. Good? All right, well, one more thing here. I could choose, if I wanted to multiply this by 1 over 6, and this by 1 over 6, if I wanted to. And again, I would get an equivalent fraction. Okay, so that's what I'm going to use. And I'll show you why I wanted that in 1 second. So this will turn into n of A and B divided by 6 all over n of B all over 6. Right? So if we multiply this fraction times that, right, we turn that into a little multiplication of a whole number and a fraction, it just gives you this. And then a denominator, it just gives you this. And then 6, isn't that the same thing as n of s? The number of values in our entire sample. That's why I happened to pick the 6. So this is the same thing as n of A and B divided by n of s divided by n of B divided by n of s. Good? And now what is this? This is the probability of A and B, and this is the probability of B. So we get to the formula. Probability of A and B all over the probability of B. Any questions so far? Did I lose people? Okay, so you never have to do these middle steps here. I did these middle steps so you can see where the formula comes from, but when you read your book, it's just going to say this, and in fact, they usually don't put this one in this order, they usually put it in the other order. So when you read your book, it'll probably say something along these lines. Probability of A given B is equal to the probability of A and B divided by the probability of B is equal to the number of outcomes in A and B divided by the number of outcomes in B. That's usually how books write it. Right? So these middle steps are just to convince you that this is equal to that or this is equal to that. Any questions? No? We're good? We're good? Solid, good. Okay. So the selection of A and B here is just arbitrary. We could have just as easily gone the other way around. So in general, we can also write it the other way around. So the other way around would be that the probability of B given A is equal to the probability of B and A divided by the probability of A. Right? So the only thing you have to be careful about is the matching. This is the one that's constant, it's fixed. There's no uncertainty about that, so that's the one that goes in the denominator. Here, if I flip it around, then this one's the one that goes in the denominator. Okay? So that's what's important. And then this is also equivalent to n of B and A divided by n of A. Good? Questions? Comments? Issues so far? No? Okay, so this is how your book gives it to you. Now the book likes to use the letters E and F. A and B, E and F, same thing, right? So this is the official formula that they give you for conditional probability. If E and F are any two events, then the probability of F given E is equal to the probability of E and F divided by the probability of E, which is equal to the number of elements in E and F divided by the number of elements in E. Well, that's a mouthful. How are we doing? Kind of, okay, sort of, maybe, sort of, maybe. Okay, all right, so let's look at another example. So we'll refer back to this formula. So let's say we have this example. A survey was conducted by the Gallup organization, conducted on May 8th through the 11th in 2008, in which 1,017 adult Americans were asked, which of the following statements comes closest to your belief about God? You believe in God, you don't believe in God, but you believe in some universal spirit or higher power, or you don't believe in either one, right? So you got three choices. The results of the survey by region of the country are given in this table. So here's the table. Let's look at this table, make sure we understand it. So in the rows, we have the possible questions they ask. Do you believe in God? Do you believe in some sort of spirit? Do you believe in neither? Okay? And it's broken down by regions of the country, the East Coast, the Midwest, the South, the West. So for instance, in the East and believe, so 204 people live in the East and believe in God in this survey. 9 people don't believe in either and live in the South. Right? That's what that's saying. And if we add them all across, then we get all the people that live in the East, all the people that live in the West. If we add them all down, we get all the people that believe in God, all the people that believe in a universal spirit, all the people that don't believe in either. Good. And we know that there was a total of 1,017. Okay. We're good so far on what that table is describing? Good? Okay, so what is the probability that a randomly selected adult American who who lives in the East believes in God? What is the probability that a randomly selected adult from this survey, not anywhere, well, if I'm using the results from this survey, it would be a proportion, but we're using this as a way of finding the true proportion of all Americans through the empirical method, right? This is empirical probability. We took some sample results, and we're going to use that information to try and approximate the theoretical probabilities that are out there. So using these results, find A. What is the probability that a randomly selected adult American who lives in the East Coast believes in God? So I feel like there are a couple of options that might seem tempting at this point. They live in the East and they believe in God, or maybe they live in the East given that they believe in God, or maybe the other way around, probability that they believe in God given that they live in the East. So which of those three is going to help us solve part A. Who lives in the East believes in God. What is the probability that a randomly selected adult American who lives in the East believes in God? So, English is tough, but, there's a lot of different ways of saying things in English. But it sounds to me like lives in the East is fixed, right? We want that to be a fixed thing. What's the probability that a selected American who lives in the East, that part is fixed, believes in God? So, this one, right? What's the probability that an adult American who lives in the East, we're setting that as a fixed thing, believes in God? So this is what we want, and now we use our formula, and our formula has that it's equal to the probability that they believe in God and they live in the East, divided by the probability that they live in the East. Right? So it's important for them to match. This is the one that goes down here. Good? Makes sense? Yes, yes, yes. This is definitely the one for part A here. Part A. Okay, but then we don't really know those things. I don't know the probability and this probability. It would be more useful for us to use the other part of our sentence here, or our definition, that it's equal to the number of outcomes that are in God and East, divided by the number of outcomes in the East. Okay? So, looking at our table, how many elements, how many outcomes, how many survey takers landed in both believe in God and they live in the East? 204. And then how many survey takers live in the East? Okay, good. So you got to add these. So you got to add 204 plus 36 plus 15, which gives us 204 divided by 200 and what? 55. And what does that result as a decimal? 0.8. 80. 80%. Okay? So given that you're going to focus your selection, given that you know that the selection, the randomly selected American, definitely lives in the East, given that you know that for sure, the probability that that person, that individual, also believes in God, there's an 80% chance.
Probably what they confused on is, like in the other problem section you went over, you said that we're able to swap them, like switch them, right?
Yes, right here. When there's an and statement. An and statement, you can definitely swap them. These two things you cannot swap in general, right? So as a general rule, you can't do that. There might be some special case where it turns out that, yeah, they're the same thing. That does happen, but not always. So you can't guarantee, you can't depend on being able to flip them. So don't flip them unless you know you're able to flip them, and we'll talk about that in a little bit.
So knowing that the one that is fixed, the people that live in the East, you would place that second and the one that you're trying to find out.
Correct. So when you read this, this is the unknown, given that this one is known. This one is fixed. You know for sure I'm picking someone from the East Coast. Now that I know it's someone from the East Coast, what's the probability that that person believes in God? Good? Questions? Okay, what about part B? What is the probability that a randomly selected adult American who believes in God lives in the East? Okay, so it's the other way around. So again, when you read that, probability that we got East and God, we got probability of God and East, and we got probability of East and God. So those are the three possible ones that might come to mind when you're reading this on a test. So, most word problems, when it's this one, will have the words and in there. So that's one key word to be looking for. What's the probability that a randomly selected American lives in the East Coast and believes in God? So usually the word and is in the middle of the word problem. very often the word given is in the word problem. But like I said, English is difficult. There's a lot of different ways of saying things. And sometimes there's a little bit of room for ambiguity. So that's what makes these problems extra fun. So part B says, what is the probability that a randomly selected adult American who believes in God lives in the East? So the who believes in God, that part is fixed. I'm going to focus on the people that believe in God. So now that I'm definitely picking someone who believes in God, what's the probability that they live in the East Coast? So now this guy is the one, right? So now this is the answer to part B. Because this part is fixed now. They definitely believe in God. Now what's the probability that they live on the East Coast? Good? Questions? Okay, so then we go through our definition again. It's equal to the probability of East and God. Probability of East and God divided by the probability of God. That sounds funny. What's the probability of God? Okay, well, we don't have probabilities in this case. We have tables. So in our particular case, in this particular word problem, it makes more sense to use the other part of our definition, which is to say it's the number of elements in those events. So this is equal to the number of elements in East and God divided by the number of elements in God, right? So how many people live in the East Coast and believe in God? Same thing as before. 204 people fall in that category. Now, how many people believe in God? Well, now we got to add them down, right? So it's got to be the 204 plus the 212 plus 219 plus 152. So that's going to give us to 204 divided by 787, and we can turn that into a decimal if we wanted to, which would be equal to, is that decimal? 259? 259, close to 26%. Okay, so how are they different? This one is saying, I'm definitely going to pick somebody who believes in God. What are the chances that they live on the East Coast? 26% almost, right? The other one was the other way around. If I know, the other one was the reverse. Here we're saying I know I'm picking someone from the East Coast. Given that I know they live on the East Coast, what is the probability that they believe in God? So that's a slightly different thing, and we saw that in that case, it was 80%. 80% chance that happens. So, in this particular situation, you notice that flipping them did not give us the same answer, right? In this particular case, we saw that the probability of God given East Coast does not equal to probability of East given God. Right? We got different answers. Here we got an 80%. Over here we had a 26% chance almost. In general, that's usually the case, that you can't just flip them around. They usually do give you different answers. There is a case where they do give you the same answer, and that's a special situation we'll talk about in a little bit. Good? Questions? So, in 2005, 19.1% of all murder victims were between the ages of 20 and 24 years old. Also in 2005, 16.6% of all murder victims were 20 to 24-year-old males. What is the probability that a randomly selected murder victim in 2005 was male, given that it was a 20 to 24-year-old individual? Good. See how they get messy? There's no Venn diagrams here. There's no tables here. All they did is give us a messy word problem with a bunch of probabilities in it. So that's when we really have to rely on our equations, right? So we have to lean on them and rely on them and know that they work, cross our fingers that they work. Okay? All right, so what are they actually asking? They're asking us to find the probability. What is the probability that a randomly selected murder victim in 2005 was male, given that the victim is 20 to 24 years old? So, probability that it's a male, given that we got a 20 to 24 year old. That's what we're after, right? Probability, find the probability that it was a male, given that the victim is 20 to 24 years old. Good? So, by my formula, I know that this is going to be equal to the probability that they're male and they're 20 to 24 years of age, years old, divided by the probability that they're 20 to 24 years old. In this case, I don't have to go to the other part of my definition of the number of elements, because I don't have any number of elements, I have probabilities. Good? Questions? Good, good, good. Okay, so the probabilities they gave us. 19.1% of all murder victims were between the ages of 20 and 24 years old. Does that look like the numerator or the denominator? That's the denominator, right? The probability that a randomly selected murder victim is between the ages of 20 and 24 years of age. Looks like that's the 19.1%. And then the other one they gave us is that also in 2005, 16.6% of all murder victims were between 20 and 24, were 20 to 24 year old males. So they're 20 to 24 years old and they were males. That's the numerator, right? That's this guy at 16.6%. Good? Questions, questions, questions? So I know that this whole thing is going to be equal to 0.166 divided by 0.191. So we can take our calculator, divide that. Uh, 8691. 0.8691. Any questions? No? So, interpreting what this means, what's the probability that a murder victim in 2005 is a male, given that you know this is true? So, picture yourself like on a police scanner, you're just listening to what's happening in the city, and like, oh, they found a murder victim. Oh man, what's happening? So you get all nosy, and you're listening, what's happening, and you're asking yourself, what do I know about this murder victim? Could it be my friend? Is it someone I know? What's happening? So you're looking for information, and you hear one of them say that the murder victim is between 20 and 24 years of age. So far, that's all you know. A murder victim, and it's someone that's between 20 and 24 years of age. Now you're asking yourself, what's the probability that it's a male? Okay? Probability that it's a male, given that you know this to be true. Well, that answer is close to 87% chance. What does that tell you about 20 to 24-year-old murder victims? A lot of them are males, right? Yes? So if I know there's a murder victim, and I know their ages range between 20 and 24, there's a very high chance that we're talking about a male, right? Males are a lot more prone to violence in that age range. Probably in any age range, right? So our general rule is that the probability of A given B is equal to the probability of A and B divided by the probability of B, right? Where it's important that these two match. Your book likes to use E and F, but A, B, E, and F doesn't matter, same thing. Okay? So what I'm going to do is a little bit of algebra magic again. I'm going to multiply both sides of this equal sign by the P of B. Multiply this side by the P of B. And then what happens? These guys cancel. And so I end up with probability of B times the probability of A given B is equal to the probability of A and B. Good? And then we just flip this guy around. It's sort of customary to write it this way. A and B is equal to this multiplication in this order. Probability of B times the probability of A given B. Good. Remember I said before that when we have an and statement, you can flip those around. That's okay. You just can't flip these things around. So this can also be written as the probability of B and A. Totally okay. This is the same thing as this, which means that this is also equal to that. Probability of B times the probability of A given B. That makes sense? Okay, so the probability that they both happen, A and B, is equal to the probability that the first one happened times the probability that the second one happened, given that the first one has happened. Kind of. Okay, and then the choice of A and B in this order here is arbitrary, so I can also flip them around and think about the other case. What is the probability that B given A? Right? And so in this case, this is equal to the probability of B and A divided by the probability of A. Right? These things have to match. Okay, and again, I can do the same algebra magic here, multiply both sides by the probability of A. And these guys cancel. So again, now I end up with the probability of A times the probability of B given A is equal to the probability of B and A. Right, I'm just really doing the same thing. And then again, it's just customary to write this in the other way around. So I'm just going to write this on the left-hand side. So this is going to be equal to the probability of B and A, which is equal to the probability of A times the probability of B given A. And then one more time, one last thing. We know that when there's an and statement, we're allowed to flip them. That's okay. So this is the same thing as writing it as probability of A and B, which is equal to this guy, probability of A times the probability of B given A. So far, everyone's with me? It's a long road. We're good? Okay, so, but isn't this exactly the same as this? And this is the same thing as this. And then I said these were equal and those were equal. So what does all of this allow us to conclude? Well, it means that this is equivalent to this. Right? They're all the same thing. Good? So I can combine it all and say that, first of all, we know that the probability of A and B, the order doesn't matter, so I know that that has to be equal to the probability of B and A, right? Me and my friend both put money down on this wager in Las Vegas. The probability that I win and he wins, well, that's the same thing as the probability that he wins and I win. He wins, I win, he wins. The order doesn't matter, we're both winners, right? So these two things are equal to each other. Flipping the A and the B when there's an and statement, perfectly okay. You get the exact same result. Okay? So now we also have that if we have the probability of A and B, that's equal to the probability that A occurs times the probability that B occurs given that A has occurred, right? Because we said it's right there. And also we have the probability of B and A happening. Well, that's equal to the probability of B happening, B has occurred, times the probability that A is going to happen, given that B has already occurred. Right there. And then finally, since this is equal to that, I can just say that these two things equal each other. Probability of A times the probability of B given A is equal to the probability of B times the probability of A given B. That's it, I promise. Intense? I told you this stuff was hard. You really got to read it, try the work, don't fall behind, because it'll leave you behind. This is how the book gives it to you. The book likes to use the letters E and F. I sometimes try and avoid E and F because when I write it on the board, my E's and my F's look very similar, and it's extra complicated if all the letters look the same. So at least my B and my A look very different. So that's why I avoid it. But, you know, it doesn't matter. They're just dummy variables. E, F, A, B, doesn't matter. So they're saying that the probability of E and F is equal to the probability of E times the probability of F given E. So the order is important on the right-hand side. Probability of E times the probability of F, given that E has occurred. Okay? The E and the F, those are the ones on the left-hand side. Those are the ones that can be flipped around if you're interested, if you wanted to, if it helps you. So here's an example. Let's get back to those murder victims. In 2005, 19.1% of all murder victims were between the ages of 20 and 24 years old. Also in 2005, 86.9% of murder victims were male, given that the victim was between 20 and 24 years old. What is the probability that a randomly selected murder victim in 2005 was a 20 to 24-year-old male? Intense, right? Okay, so I would suggest you begin breaking this problem down by focusing on what they're asking you. What is the end goal here? What is the question that they want? So stick, going down to the bottom there. What is the probability that a randomly selected murder victim in 2005 was a 20 to 24-year-old male? So they're talking about this. They're talking about the probability that we have a 20 to 24-year-old male. So male and 20 to 24 years old. Good. And from my formulas, I know that that's equal to, it's equal to the probability that they're male times the probability that they're 20 to 24 years old, given that they're male. Right? That was my formula. This is similar to this guy. That is similar to this guy here that we have A and B. So A and B, it's A given that B, right? So the probability of A and B is equal to the probability of A times the probability of B given A. Let's assign the letters for this guy. So this can be considered as our A, this can be considered as our B, this is considered as an A, this is the B given the A. All right. Probability of A in the male, A and B, where B is the 20 to 24 years old, is equal to the probability of A times the probability of B given A, or using the language of this particular word problem, we get that. Okay? Also, we learned that these two things can be flipped around. So I could also say that this is the same as the probability that they're 20 to 24 years old and male. Does it make sense why switching those two things around shouldn't matter? I'm looking for the probability that a murder victim is a 20 to 24-year-old and male. That should be the exact same thing as the probability that it's a male and they're 20 to 24 years old. That shouldn't matter, right? And it doesn't matter. We get the same answer. Okay? Now where it matters is over here, because this has to be in this order. It's got to be male times 20 to 24-year-old, given that they're male, right? Given that, because we've already established that up here. Okay? So now this one is going to be equal to the probability that it's a 20 to 24-year-old times the probability that they're a male, given that they're a 20 to 24-year-old. Good, good, good. You can't mix and match these. That's the one place where you can't do that. So you can't take this and stick it up there and say male times male given. That'll give you the wrong answer. And you can't take this and bring it down and set it next to this thing. It doesn't. That doesn't work either. These this stuff here on the right hand side, the order is important. Exactly the way it's written is important. So this first times this given that. Good. And in terms of the A and B thing again, if we're sticking to this, then the A is over there now, the B is over here. The probability of B and A is equal to the probability of B times the probability of A given B. Yeah, question?
So just looking at the right-hand side of the equation, all the terms on the right-hand side of the equation, could they be switched between those two? As long as it's a whole unit?
So let me write down the things you cannot do. So you cannot say that it's equal to the probability of male times the probability of male given 20 to 24 years old. Right? That's not true. Because male came first, and now we need this to come and then given male. So the order becomes important there. Okay? So these two have to be together in that order. These two have to be together in that order. Now on the left-hand side, these two things could be switched. That's okay. Right? And they will equal the same thing. Right? So there is some number that belongs there, some number that belongs there, such that when you multiply them together, they give you that answer. And then there's also these two other numbers here, such that when we multiply them, they give you that answer. And these two are the same answer. Once in a second, we'll put in some actual numbers in there, and we'll see what those values are.
I skipped over, but
Yeah.
the second line, where 20 to 24-year-old on B, that goes to the left a little bit. Now, how did that change from male and A at the top to B right there?
So what I did was, I'm sticking to the notation that A is the male and B is the 20 to 24-year-old. So up here, I have it in this order, A and B. So therefore, it's equal to the A happening times the B happening, given that it's the A. So now, if I decided to switch this, let's just flip it around just for fun. We're allowed to do that. If I wrote it as B and A, just to flip it around, then that's fine, but you also have to be consistent over here. This guy comes first. The probability of B, this guy came first, times the probability of this one, A, given that B has already occurred. Good, good. All right, so now let's read through our word problem. What this means is that we have two choices. This is what they wanted us to find, the probability of male and 20 to 24 years old. And I got two ways of finding that, either through this multiplication or this multiplication. So it's just a matter of a word problem of which one they've given me enough information to be able to use. So reading it, 19.1% of all murder victims were between the ages of 20 and 24 years old. Which one did they give me? Right here, right? This is the one they've given me. This is 19.1%. This guy is 19.1%. Okay? And hopefully they gave me this one. Because if they gave me one of those, then I'm in trouble. Like if the next thing on this word problem says the probability it was a male is 13%, oh, can't answer it. Not enough information, right? I need these two or I need these two. That's how I can answer this question. Got it? Okay, so the next part says, in 2005, 86.9% of murder victims were male, given that the victim was between 20 and 24 years old. Ah, isn't that this? Male, given that they were between 20 to 24 years old. They did give me exactly this one. So this guy is 86.9%. They gave me the two that I needed, which is good, because then I can solve it. If this word problem had said the other way around, there's an 86.9% chance that the murder victim is 20 to 24 years old, given that they're male, they had given me this one, then I'm in trouble. I can't solve it. Good? Questions? No? No? Okay. So that means that if we multiply these two things together, we'll get that one. So let's go back over here. So then I can say that the probability, let me erase this thing. So this is going to be equal to 0.191 times 0.869. And what is that? Can we multiply them? Oh, sorry, 0.16? 0.165? So 16.5%? Yes? Good? Yes? Okay, so we're done with this question. This is the answer for this question. Right, so probability that it's male and that it's a male victim, murder victim, between the ages and is also between the ages of 20 and 24 is equal to the probability that they are between 20 and 24 years old times the probability that they're male given that they're between the ages of 20 and 24. That's what we wrote down here. And so now we get that. That's our answer. Good. So we're finished answering this question. Let me just throw in one more thing. What if I told you that the probability that a murder victim of any age, just a murder victim, is a male, and I told you that that probability is, make one up. I'm just making one up right now. So let's say the problem says it extends to a question, this is part A. Let's say part B of the problem says, if the probability of being male is equal to, so a murder victim in 2005, what do you think it is? Do you think it's 50-50? A murder victim, male, female, what do you think? More males get murdered, more females, is it the same? What do you guess? More? I'm guessing right now, just throw one out there. 71. So let's say that this is part of the word problem. If the probability that a murder victim in 2005 is male is 71%, find the probability that it's a 20 to 24 year old given that they're male. Okay? Alright, so now let's look at this flow chart here. These two things are equal to each other, right? And we already found this, and we have this. This was given to us, this was given to us. I multiplied it, that means that this is 16.5%, which means that this is also 16.5%. And now if they're giving me this one, I can find that one. You see that, how that whole flow chart goes? Okay, so in order to find that one, if I know this one and I know that one, let's just put them on here. If this is 16, that means that this guy over here is 0.165. And if the part B of this question said that this was 0.71, then I can find that one. That's easy. All I have to do is divide them. Got it? So the answer would be then the probability that it's a 20 to 24 year old given that they're male is going to be equal to 0.165 divided by 0.71. So that would be 0.165 divided by 0.71. So this would be equal to 0.2324. Good? Questions, comments, issues? So now we can go back over here and finish this little cycle here. This is saying that this, oops, put it in blue. This is saying that this part right here is 0.23, we'll just round it to 23. Okay, so my point with this was, notice that these numbers are different. This number, 71%, is different than the 19%. This number is different than that number. But what we are saying is that when we multiply them together, they give you the same result. They both equal to 16.5%. Any questions? Any questions? And that's why you can't mix and match them. You can't grab this one and this one. You can't grab this one and this one. It has to be these two. And it has to be these two in that order. Okay, so in this example, a study involved foreign and domestic mammals as shown on this table. So we have mammals, birds, reptiles, amphibians, and the animals were either U.S.-based animals or foreign animals. So we have this nice table. So in order to be able to figure out the total of animals were from the U.S., we'd have to add them across, right? Or how many birds we had in the study, we add them down. So we fill out the table, going across, going down, and then the totals should add up to 663. Good? We're good with that part? Good? Okay. So let's answer some of these questions. The first one is the probability that the animal is foreign given that the animal is a reptile. Foreign given that it was a reptile. Probability that we got a foreign given that it was a reptile. Okay? So by the definition of conditional probabilities, we know that this is going to be equal to the probability that it's foreign and a reptile, divided by the probability that it's a reptile. It's got to match with this guy down there. That's the definition of it. And well, we don't have probabilities here, so that's not very helpful, but we have another version of the same rule that says that it's also equivalent to the number of outcomes in foreign and reptile divided by the number of outcomes in reptile. Good. Okay, so by our table we can see that the number of animals that were both foreign and a reptile is equal to 64, and then the number of reptiles altogether was 78. Okay, so now we can take that and divide them, and what do we get? We get 64 divided by 78. I'm getting 0.82. What is the probability that it's a reptile given that it was a foreign animal? Probability of reptile given that it's foreign. So then this would be equal to the probability that it's a reptile and foreign divided by the probability that it's a reptile. I'm sorry, probability that it's foreign. And again, we don't have those probabilities, so we like to use the other version of this, which is equal to the number of outcomes in reptile and foreign divided by the number of outcomes in foreign. Good? Questions? Okay, so now how many are in? Well, that's the same thing as over there. So this is still equal to 64 in the numerator. But now it has changed, the denominator is different. Now the denominator is going to be 498. So we do get a different answer. So it's going to be 64 divided by 498 is equal to 0.1285. So what is the probability that it's a bird or amphibian given it's from the US? Probability that it's a bird or amphibian given that it's from the US. So now we can jump to the probability of bird or amphibian divided by the probability that it's from the US. So this is going to be equal to the probability of bird or amphibian as a little unit, and also from the US, divided by the probability that it's just from the US. Good. And again, this isn't a word problem that has probabilities just given to us. We have all these table values, so we want to use the other version, which is the number of outcomes that are in bird or amphibian as a little unit, and from the US, divided by the number that come from the US. So from our table, the denominator is easy. That's how many come from the US. That's going to be 165, right? And now bird or amphibian and the US. So both things have to be satisfied. All the things that are birds and from the US, all the things that are amphibians and from the US. So we have the 78 that are birds that are also from the US, and we also have the 10 that are amphibians and from the US. So this would be a little summation of the 78 plus the 10, right? The 10 that are birds and from the US, the 78 that are birds and the US, and the 10 are amphibians and from the US. So our answer is going to be equal to 88 out of 165, which turns into 0.53. So the next one is the probability that the animal is foreign, given that the animal is a mammal. Probability that it's foreign, given that it's a mammal. Alright, well, I'm going to skip that middle description of probability, as we've seen a couple of times. It's there. In other word problems it might be useful, but clearly in this one we have a table, so we'd like the part of the definition that involves the number of elements. So this is just going to be equal to the number of outcomes that are both foreign and mammal, divided by the number of outcomes that are mammals. Okay. And so from our table, we see that the number that are foreign and mammals is equal to 251, divided by the number of mammals, 314. Right? And if we wanted to, just for fun, we could do the other way around. Right? Probability of a mammal, given that it's definitely foreign, well, that's going to be equal to the number of mammals and foreign and mammal, divided by the number of foreign. So the number of foreign and mammal, well, in this statement we can flip them around, that doesn't matter. So we're still going to end up with a 251, right? Foreign and mammal, mammal and foreign, that doesn't matter, they're the same. So that stays the same, but what changes is the denominator. So now we want the total number of foreign, and the total number of foreign is 498. So when we have foreign given mammal, we have this fraction, which is 251 divided by 314, which gives me 0.7994. On the other hand, when we flip them around, I get 0.5040. Right? So we're doing this because to point out that the order matters. You get a different answer sometimes. Now there will be times where in fact you get the same answer. We'll look at those in a little bit, but not always, so you can't just rely on being able to flip them. Okay, good. Questions? The top one answers the question, what is the probability that it's foreign given that it's mammal? Whereas the bottom one says, what's the probability that it's a mammal given that it's foreign? Right, so this is the part that is constant. There is no more ambiguity about it. This is given to you. And this is the thing you're trying to find a probability for. Right, so the probability of mammal given that it's foreign versus the probability that it's foreign given that it's a mammal. So they sound very similar, but they do have different answers. Okay, good. Probability that it's a bird and reptile. What's the probability that it's a bird and a reptile? Can that happen?
No.
Is it possible that one animal is a bird, but it's also a reptile? No. So this is just going to be 0, right? Can't happen, 0. Okay. So what about the probability that it's a bird or a reptile? Probability that it's a bird or a reptile. Well, by using our formula, we know that this is equal to the probability that it's a bird plus the probability that it's a reptile minus the probability that it's a bird and a reptile. And as we just saw a second ago, this can happen, that's 0. That means that the event it's a bird and the event it's a reptile are disjoint. So this means, this leads us to conclude that event bird and event reptile are disjoint. Good? You're good? Okay, so now it just simplifies to these, so I can just find these two probabilities separately and add them together, and that'll give me the answer to the probability it's a bird or a reptile. So looking at our table, what's the probability that it's going to be a bird? That's going to be the number of birds divided by the number of values in our sample space, or 253 divided by 663, plus the probability that it's a reptile, that's going to be equal to 78 divided by 663, which gives me a total of,
331.
what is it?
331.
331 divided by 663, which turns into 0.4992. 4 decimal places. Okay, any questions on this? Probability that it's a mammal and from the US. What's that going to be? So mammals and from the US, there are 63 that qualify under both conditions. So this is equal to 63 divided by 663. Good. I'll leave it as a fraction for now. You can also turn it into a decimal. But now that we have that, now we can answer the other question. What is the probability that it's a mammal or from the US? Probability that it's a mammal or from the US. So by our formula, we know that this is equal to probability that it's a mammal plus the probability that it's an animal from the US minus the probability that it's a mammal and from the US. Good? Okay, so the probability that it's a mammal by itself, well, there are 314 mammals total divided by 663 plus the probability that it's from the US. Well, there are 165 that qualify as from the US over 663, minus the probability that from the US and their mammals, that would be 63 out of 663. So we can just tuck this under one big happy fraction. 314 plus 165 minus 63 divided by 663, which gives you
116.
416 divided by 663. Yes? Yes. So what is that as a decimal? That's 416 divided by 663. So 6275. 0.6275. Good. Any questions about this one? Good. Okay, so this was derived using the formula for an OR statement. So when you see an OR statement, you should be thinking addition, right? The addition rule for probabilities involves an OR statement, one or the other. It's going to involve addition. Sometimes it involves the addition and then we have to consider the subtraction of the overlap. But if they're disjoint, then this becomes 0 and then it just becomes simpler. Okay? Now, in this particular case, since we have a nice little Venn diagram, then we don't have to do it this way. We could just count things, right? So if we're just looking for all the animals that qualify under one condition or the other condition, then we can just identify them up there and we can come up with a couple of shortcuts, right? One shortcut could be to just add them all together, and so I can identify the following. So the probability that it is a mammal or from the US, just by looking at my table, I could say that let me write down all the animals that qualify under one condition or the other condition. So that would be the 63 plus the 78 plus the 14 plus 10. Those are all the ones that are from the US. And then there was an additional plus 251 that were mammals that haven't already been counted. And I know all of that is divided by 663, right? That's just by looking at the Venn diagram, right? So that should give us the same answer of 416 divided by 663. Good. Okay, another shortcut from the table again, also you could say that, well, I already know what the whole thing at the top adds up to, so why do it again? I know that all of these are going to be equal to the 165, so I could do 165 and then just add the 251 over 663. That's going to give me the same answer, 416 over 663. So that's another quick shortcut. Just add one whole column across like this, one whole row across, and then add the one that's missing. Or you can do it the other way around. I could add the 314 and then just add the 78, the 14, and the 10. Since I know that coming down that all the mammals are 314, and then all I have to do is add the rest of them, which is the 78 plus the 14 plus the 10. Again, all of that over 663. And again, any way you slice it, you get the same answer. Any questions? So all of this was 6275. 0. All of them lead the same answer is 0.6275. Any questions? Any questions at all? No? Okay, so, let's take a look at this one now. So say we have a full deck, a standard deck of cards. We know there's 52 cards. There are 4 suits. We got clubs, diamonds, hearts, spades. Each suit has 13 cards. Okay, so the question says, what is the probability that a card drawn is a queen? Okay, so let's do that one first. What's the probability that one card is drawn out of the 52 and we get a queen? 4 out of 52, right? There are 4 queens in the deck. there's the queen of clubs, queen of diamonds, queen of hearts, queen of spades, 4 queens, 52 cards. That's our answer. We can reduce this into 1 out of 13, and we can turn that into a decimal, 1 divided by 13, into 0.0769. Stop there. 69. 0769. Okay. So your friend draws a card, right? And looks at it and tells you, just kind of gives you some additional information. It tells you, I'll give you a hint. The card I drew is a heart, right? So initially, your chances of selecting the queen were 4 out of 52. But now, 1 card has been drawn, and now you have additional information that it is definitely a heart. So the question is, what's the probability that it's a queen? Okay. So what's the probability that it's a queen, given that we definitely know that it was a heart? Okay. So this is equal to the number of outcomes in queen and heart divided by the number of outcomes in heart. So how many ways are there for me to have a queen and a heart? 1, right? There's only 1 card that is a queen and a heart. And how many ways are there to get a heart? 13. Oh, it's the same as that one after we reduce it. And so therefore we ended up with 0.0769. Right? So we got the same answer. Got a question? Do you have to reduce it? No, I only reduced it in this case because I wanted to get to the point where I see that they're the same. So I was just kind of doing that. But in general, I don't like reductions. I prefer to see it that way so I know where you got your answer from. So write it as a fraction and then turn it into a decimal. But I was just doing it for the purposes of seeing that they're the same thing. Good? Any other questions so far? Yeah. Which part? All of it? Or?
No, the second part. Just the second part.
Queen given heart. So since we know it was definitely a heart, right? So the scenario is that you're going to choose 1 card out of the deck, and you're guessing, maybe you're betting money, you're putting money down that it's going to be a queen. So initially, you're thinking my odds of winning are 4 out of 52. Okay? So you put some money down, you pull out a card, and now, you know, the guy's peeking at it, and he goes, I'll give you a hand, it's a heart. Okay? So you're not getting a new card. This is not about doing another experiment. It's just that you're getting additional information about that 1 card. So now your friend says, I'll give you a hand, it's a heart. And you're thinking, okay, how does that help me or hurt me? What does that do? Well, you calculate your new probability of getting a queen, given that now you know that the card selected was definitely a heart. And so as we see, it turns out that it makes no difference in this case. In this particular situation, as we described it, the fact that you were given the information that it was a heart, it didn't really help you. We're good? What if instead of him saying, I'll give you a hint, it's a heart, what if he says the opposite? You know, you pull out 1 card, he looks at it and goes, I'll give you a hint, it's not a heart. The opposite, right? So, what's the probability that it's a queen, given that he told you that it was not a heart? Now we can write not a heart this way, like that. Or we can also write it as probability of queen, given heart, with like a bar above it, right? The complement of it. We can also put a little C there to represent that, but not heart. Either way you like to write it, I'm going to go with this one here. So this is equal to the number of ways in which you can have a queen but not a heart, divided by the number of ways in which you can have not a heart. So this would be n of queen and not a heart, divided by the number of ways in which you can have not a heart. Okay, so if we examine our deck, there are 52 cards total, 4 suits. So not a heart means it was one of the other 3 suits. Each suit has 13 cards. how many cards are there that are not a heart? 39. So by him giving you that hint, like I'll give you a hint, it's not a heart, he's letting you know that it's one of these 39 cards. You have additional information now. So now that you have that information, how does that affect your probability of getting a queen? Well, how many queens are possible in that 39? 3. So we got 3 out of 39. And when we reduce that, we find that again we get to 1 out of 13, which again is equal to 0.0769. Okay? All right, so what is happening? Let me write this down in this notation. So we found that the probability of having a queen, given that we were told it was a heart, is equal to the probability that it was a queen. Either way you calculated, you were getting the same thing, 1 out of 13, right? Either way. So the fact that this was given to you didn't change anything. It didn't help you, it didn't hurt you, it made no difference, right? You might that wasn't a helpful hint in any way. Does that make sense? So we can say that these two things are independent. So if we go back to the definition of independence, which we did a while ago, the first time you saw it, maybe it didn't quite click in, maybe it helps a little bit more. Two events, E and F, are independent if the occurrence of event E in the probability experiment does not affect the probability of event F. Isn't that what just happened here? We have two events. We have event, it's a queen, and event, it's a heart. We have two events, but now we are told event heart actually happened. It definitely happened. How does that affect event queen? It's a queen. It didn't affect it at all. So if that's the case, that means that those two events are independent, right? So event, a queen is selected. That's one event. Another event could be a heart is selected. We have two events here. Event 1, it's a queen. Event 2, it's a heart. So what we just discovered that when we're dealing with the event, it's a queen, if we have the additional information that in fact this event happened, it had no effect on it. That's the definition of two things being independent. Good? Questions, comments, issues? So we can conclude that event queen was selected and event queen and event heart are independent. Sort of, kind of, maybe, sort of, kind of, maybe, no? What if we had flipped it around? What's going to happen there? Just for fun, let's see. What if you are going to draw a card from the deck and you're going to put some money down? You're like, I bet it's going to be a heart. Right? You're going to flip it around. So you bet it's going to be a heart, and then the card is drawn, and your friend peeks at it, and they're like, I'll give you a hint. It's the queen. So it's the other way around. Does that affect things? So now we want to look at the comparison between these two. Probability that it's a heart. Right? Initially, I'm putting money down. I'm betting it's going to be a heart. So initially, I know that there are 13 cards that are hearts out of 52. That's 1 out of 4. That's my initial that's my initial probability of being correct, right? So then you draw that card, and your friend's like, I'll give you a hint. It's a queen. All right, how does that affect your life? Does that change that probability? So now we get that the probability that it's a heart, given that you definitely know that it's a queen, is equal to, well, now that you know that it's definitely a queen, there's only 4 options that could be. Queen of hearts, queen of diamonds, queen of spades. Okay, so 1 out of 4. Same thing as before. Once again, we have a situation where even though you have additional information, it changed your life in no way, shape, or form, right? It didn't make it better, and it didn't make it worse. It stayed the same. So, again, we can conclude that those two events are independent. Good? Good, good, good. Okay, how about if we looked at another case? How about this time, I bet that it's going to be a number that's odd. Let's make it a little bit more interesting. I'm going to bet that it's an odd number. Event, an odd number is selected. Okay. So what are the things that constitute an odd number? So we can say it could be like, well, there is no ones in the deck, right? I'm not going to consider an ace to be an odd number. So we have 3s, or we have 5s, or we have 7s, or we have 9s. That's it, right? As far as the numbers. But then for each one of them, there are 4 suits. It could be the 3 of hearts, or the 3 of clubs, or the 3 of diamonds, or the 3 of spades. Wow, that's terrible. Okay, so there are 4 of them for each, or these. So total, how many are there going to be? Total of 16. Okay, so I'm betting that it's going to be an odd number. So the probability that it's an odd number, probability that it's odd, is going to be equal to 16 out of 52. So the same thing happens where you draw a card, you're betting that, but now your friend gives you a hint again. They pull out a card, he looks at it and says, I'll tell you what, I'll give you a hint. It's a face card. Okay? A face card. Does that affect the probability of being odd? Probability of being an odd card, given that your friend just told you that it's a face card. Doesn't affect your life? My chances of winning before he told me anything were 16 out of 52. What do I got? That's 16 divided by 52. That's equal to 0.3077. I had a 30% chance of winning, almost 31% chance of getting it right. But now that he gave me a hint that it's a face card, what are the chances I could win? What are face cards? Jacks, queens, kings, right? So how can I get an odd number? If he told me, I'll give you a hint, it's a face card, probability of winning now is 0. Did it get affected? Did this new information affect me? It did affect me. Okay, so these two events, odd and it's a face card, are definitely dependent. Okay, so event odd and event it's a face card are dependent. Any questions about that? No? So if the additional information changes the probability, either making it better or making it worse, it just makes it different, then those two things affect each other, they're dependent on each other. If the other case, they did not affect each other, the probability stayed the same, then they stayed independent. Okay? So that leads for a test of whether something is dependent or independent. If you want to know if two events are dependent or independent, you're going to have to do this kind of a test. So two events, E and F, are independent if the probability of E given F is equal to the probability of E, or equivalently, the probability of F given E is equal to the probability of F. Right? So here we're showing that it made no difference to have that additional information. So the test says that the probability of E given F, right? So if you're trying to find the probability of E given F, but it turns out that this is just equal to the probability of E, the fact that you have the information of F made no difference, then that means that E and F are independent, right? It did not affect it. Or if you flip it around, right, the order doesn't really matter. If you're trying to find the probability of F given E, and it turns out that that's equal to the probability of F, the additional information that E occurred has no effect, then either one of these leads us to the conclusion that E and F are independent. Oh, I should say events. Events E and F are independent. If that fails, if in fact it is that this does not equal that, or the other way around, this does not equal that, then we'd say E and F are dependent. Good? Questions, comments, issues?